Could Apis collide with Earth? A new study has presented a surprising perspective on asteroid Apis, suggesting that while it's currently on a safe path, a minor collision with another space object could potentially shift it onto a dangerous trajectory toward Earth. This is significant because Apis will come extremely close to Earth in 2029, just 20,000 miles away, closer than some satellites. Earlier calculations ruled out any impact in 2029, 2036, or 2068. But this new insight highlights the unpredictable nature of space and the need for continuous monitoring. In this video, we'll explore the recent study's findings on Apis, what the 2029 flyby could teach us, and how this affects our planetary defense strategies for the future. A recent study led by Canadian astronomer Paul Viert has introduced a thought-provoking scenario regarding asteroid Apis. While its orbit is currently considered safe for at least the next century, Viert's research suggests that even a small collision with another space object, such as a minor asteroid or space debris, could alter Apis' path. This could potentially send it on a dangerous trajectory toward Earth. Using computer simulations, Viert's team examined the likelihood of such an event occurring before Apis' close flyby in 2029. They found that an object as small as 2 feet, 0.6 meters, could shift Apis' path enough to bring it into a keyhole trajectory, a specific gravitational path that could lead to an impact in the future. Though the odds are extremely low, estimated at less than 1 in 2 billion for an impact in 2029 and less than 1 in a million for a delayed impact, this research emphasizes the unpredictable nature of space. Minor nudges from collisions could have significant consequences, highlighting the need to monitor not only large near-Earth objects, NEOs, like Apis, but also smaller objects that could indirectly become threats. Agencies like NASA's Planetary Defense Coordination Office use a mix of radar, optical telescopes, and space-based observatories to track these objects with high accuracy and mitigate potential risks. This study underscores the necessity of continuous advancements in planetary defense. For example, NASA's Double Asteroid Redirection Test, DART, mission successfully altered an asteroid's course by crashing a spacecraft into it, demonstrating proactive strategies to protect Earth. Such efforts are vital for understanding the complexities of asteroid dynamics and developing effective methods to prevent potential impacts, even if they seem improbable today. By considering all possible scenarios, including unlikely but possible events like those suggested in Viert's study, we can better prepare for any asteroid threats that might arise. Since its discovery in 2004, Apis has been a central focus for scientists due to initial calculations that suggested a possible collision with Earth in 2029. At approximately 1,100 feet, 340 meters, in diameter, Apis was classified as one of the most hazardous asteroids due to its potential to cause regional devastation. It was given a level 4 on the Torino Impact Hazard Scale, the highest rating assigned to any asteroid at the time by NASA. As more data became available, astronomers refined Apis' projected path using advanced radar and ground-based telescopes, ultimately ruling out any risk of impact in 2029, 2036, and 2068. However, the close flyby on April 13, 2029, remains a significant event. Apis will pass within 20,000 miles, 32,000 kilometers of Earth, closer than some of our geostationary satellites. This unprecedented proximity will allow observers in parts of Europe, Africa, and Asia to see it streak across the sky. The event provides a rare scientific opportunity to study an asteroid of this size up close and gather valuable data on its dynamics. This flyby offers a unique chance to observe how Apis interacts with Earth's gravitational pull, which could slightly alter its orbit and rotation. These observations are critical for refining models that predict the trajectories of other potentially hazardous asteroids. Such data is vital for improving impact predictions and developing strategies to mitigate risks from future asteroid threats. The close encounter serves as a real-world test of our planetary defense capabilities and our understanding of asteroid behavior in near-Earth space. From May 2021 until 2027, Apis will remain positioned in the daytime sky, making it nearly impossible to observe with ground-based telescopes. When it reappears in the night sky, astronomers will have a limited opportunity to gather critical data to confirm its orbit and physical characteristics, ensuring no unexpected changes have occurred that could alter its future path. This verification is essential for maintaining confidence in our current models and ensuring Apis remains on a safe trajectory. The 2029 flyby will allow for more precise observations. As Apis passes so closely, Earth's gravity could induce asteroid quakes, seismic vibrations that reveal information about the asteroid's internal structure. Understanding these effects is vital for improving our impact mitigation strategies. Ground-based radar, optical observations, and potentially spacecraft observations will be essential to capture detailed data on Apis shape, surface features, and spin state. This information will refine our models of neodynamics and impact prediction, providing a better foundation for future planetary defense. To expand on this, NASA and ESA are planning a mission called OSIRIS-APEX to study Apis after its 2029 flyby. Building on the OSIRIS-RX mission's success in returning samples from asteroid Bennu, OSIRIS-APEX will focus on examining Apis' surface composition, internal structure, and response to Earth's gravitational forces. The data collected will help develop more effective planetary defense strategies, such as using kinetic impactors or gravity tractors to change an asteroid's path. Observing how Apis behaves during its close encounter will help scientists test these methods and enhance preparedness for any future threats. For further context, Apis is not the only asteroid of concern. Asteroid 1950 DA, for instance, has a small probability of impacting Earth in the distant future. Studying multiple NEOs like Apis and 1950 DA allows scientists to compare their trajectories, behaviors, and responses to gravitational forces, deepening our understanding of how to manage and potentially redirect hazardous asteroids. Long-term monitoring of Apis and other potentially hazardous asteroids such as 1950 DA remains essential. Each close approach offers new opportunities for observation and study, helping scientists detect any changes in the asteroid's orbits or behaviors over time. This ongoing data collection is vital for ensuring we are prepared for any unexpected developments as we refine our planetary defense strategies. Through these studies, international collaboration and technological innovation will be key to building a robust defense system against potential asteroid impacts, ensuring a safer future for Earth. The monitoring of near-Earth objects, NEOs, like Apis has become an increasingly critical aspect of planetary defense as our ability to detect and predict their behavior improves. Advanced technologies and international collaborations are key in these efforts, providing valuable insights into the characteristics and trajectories of potentially hazardous asteroids. One of the most promising developments in this field is the deployment of space-based telescopes, which offer significant advantages over ground-based observatories. Space telescopes, such as the upcoming James Webb Space Telescope, JWST, and the NEOWISE mission, have the capability to observe asteroids and comets with minimal atmospheric interference, resulting in clearer and more precise data. Moreover, the development of infrared observation techniques has been particularly effective in identifying asteroids that are otherwise too faint to detect in visible light. Infrared observations help determine the size, composition, and surface properties of asteroids, which are crucial for assessing their potential threat level. For example, the NEOWISE mission, part of NASA's Wide Field Infrared Survey Explorer, WISE, has been instrumental in discovering and characterizing a large number of asteroids and comets. By analyzing the thermal emissions from these objects, NEOWISE has provided valuable data that enhances our understanding of their physical properties and orbits. In addition to space telescopes, ground-based radar systems play a pivotal role in tracking NEOs. Radar observations allow scientists to obtain high-resolution images of asteroids, providing detailed information about their size, shape, rotation, and surface features. The Arecibo Observatory in Puerto Rico, before its collapse in 2020, was one of the primary facilities for radar observations of asteroids. Currently, the Green Bank Telescope and the Very Large Array are among the key ground-based facilities continuing this important work. These radar observations are crucial for refining our predictions of an asteroid's trajectory and understanding its potential impact risk. One notable advancement in the field of planetary defense is the development of the SpaceGuard Survey, a comprehensive program designed to identify and track all potentially hazardous asteroids. The program's goals include detecting objects that are at least 140 meters in diameter, which could pose a significant risk to Earth if their orbits intersect with our planet. The SpaceGuard survey has already made significant progress, but continuous funding and support are necessary to maintain and expand these efforts. The survey's achievements underscore the importance of ongoing investment in asteroid detection and tracking technologies. In recent years, the international community has recognized the need for collaborative efforts to address the threat posed by NEOs. The International Asteroid Warning Network, IAWN, and the Space Data Association, SDA, are examples of collaborative initiatives that bring together space agencies, scientists, and researchers from around the world. These organizations work together to share data, coordinate observations, and develop response strategies for potential asteroid threats. By pooling resources and expertise, these collaborations enhance our ability to detect and respond to NEOs that could pose a danger to Earth. Another critical aspect of planetary defense is the development of mitigation strategies to address potential impacts. Various techniques have been proposed and tested to alter the trajectory of an asteroid if one were found to be on a collision course with Earth. These techniques include kinetic impactors, which involve sending a spacecraft to collide with the asteroid and change its course, and gravity tractors, which use the gravitational attraction of a spacecraft to slowly nudge the asteroid off its path. The success of NASA's DART mission demonstrated the feasibility of kinetic impactors, providing valuable insights into how such a technique could be used in a real-world scenario. The concept of a planetary defense shield, while still theoretical, is also under consideration. This idea involves deploying a network of space-based assets, such as telescopes and interceptors, to continuously monitor and protect Earth from potential asteroid impacts. While such a system would require substantial investment and international cooperation, its development could significantly enhance our ability to detect and respond to asteroid threats. The role of public outreach and education cannot be overlooked in the context of planetary defense. Increasing public awareness about the risks posed by asteroids and the importance of monitoring and mitigation efforts helps build support for these initiatives. Organizations like the Planetary Society and various science communication platforms work to educate the public about the science of asteroids and the steps being taken to protect Earth. Engaging the public in these efforts fosters a greater understanding of the challenges involved and encourages support for continued research and funding. The study of asteroids also offers valuable scientific insights beyond planetary defense. Asteroids are considered time capsules from the early solar system, preserving information about the conditions and processes that shaped our cosmic neighborhood. By analyzing asteroid samples, scientists can learn more about the formation of planets, the evolution of the solar system, and the origins of organic molecules that may have contributed to the development of life on Earth. The OSIRIS-RX and Hayabusa 2 missions, which returned samples from the asteroids Bennu and Ryugu, respectively, have already provided groundbreaking information in this area. Furthermore, studying asteroids can contribute to our understanding of potential resources in space. Many asteroids contain valuable metals and minerals, such as platinum, nickel, and rare earth elements, which could be utilized in future space missions and technologies. The concept of asteroid mining is gaining traction, with private companies and space agencies exploring the feasibility of extracting resources from asteroids. This emerging field has the potential to revolutionize space exploration and resource utilization, offering new opportunities for scientific and economic advancement. In conclusion, the ongoing efforts to monitor, study, and protect Earth from asteroids involve a complex interplay of advanced technologies, international collaboration, and scientific research. By leveraging space-based telescopes, ground-based radar systems, and innovative mitigation strategies, we can enhance our ability to detect and respond to potential asteroid threats. Public outreach and education play a crucial role in building support for these initiatives, while the scientific study of asteroids offers valuable insights into the history and potential resources of our solar system. As we continue to advance our capabilities in planetary defense, it is essential to foster international cooperation, invest in cutting-edge technologies, and engage the public to ensure a safer future for our planet.